for accepting our offer to give a seminar today, Amalio. I'm just going to give just a very brief introduction to your talk, and you can go ahead. So for those of you who don't know, Amalio Fernández Pacheco, he was born here in Zaragoza in 1981, and he did both his undergraduate and his PhD here at the University of Zaragoza. He did his PhD under the supervision of Ricardo Ibarra and Jose Maria de Teresa. But for the last 11.5 years, he's been carrying out his research in the United Kingdom, first as a postdoc in the group of Russell Coburn, and then as a principal investigator since 2014. So, I mean, first of all, he went to the United Kingdom to Imperial College London, and then shortly thereafter, I think you transferred to the Cavendish Laboratory. Is that right? At Cambridge?
That's correct, yes. Yeah.
And he was there for 8 years in the Cavendish Laboratory. And since 2018, he's been at the University of Glasgow, which is my alma mater, where he's currently senior lecturer. But fortunately for us, and unfortunately for Glasgow, he's moving back to Zaragoza at the end of this year with a position of Científico Titular, which is a tenured senior scientist position here in the Spanish National Research Council, the CSIC. So Amalio's received lots of awards. He's had starting from his PhD, the Springer Thesis Award. He's been a Marie Curie Fellow, an EPSRC Early Career Fellow. He's also been a Winton Advanced Research Fellow and a Fellow of Sydney Sussex College of Cambridge. And very recently, well, just last year, he received an ERC Consolidator grant, which is starting this autumn in October here in Zaragoza. So Amalio's research is focused on nano-magnetism and spintronics, and particularly on three-dimensional artifacts, which is the focus of this talk. So he uses a wide range of characterization, magneto-characterization techniques and electron and X-ray microscopy techniques, which is going to be really interesting for all of us here at the INMA. And so his talk today is going to be on three-dimensional magnetic nanostructures, a promising route for future computing technologies. So once again, thanks very much, Amalio, for giving the talk today. And please go ahead and you can share your screen whenever you feel. Right.
Well, thank you so much, Scott. First of all, I just wanted to double check that you can see my screen correctly?
Perfectly.
Yeah. Okay, very good. Okay,
well, I should just say before you start, sorry, if anyone does have any questions, please just write them in the chat and we'll establish an order afterwards. Okay, thanks very much. Sorry.
Yeah, no problem. Okay, thank you so much, Scott, and thank you everyone at INMA for the kind introduction. So as Scott was mentioning, I'm going to present today a talk about three-dimensional magnetic nanostructures, a promising route for future computing technologies. So I have designed this talk for a broad audience, more like a colloquium, given the broad range of scientists that may be attending. So as Scott mentioned, I am currently at the University of Glasgow, but a lot of the work that I will present today was also done at the University of Cambridge while I was there, but also by some of my group members that still remain in Cambridge. During the last few decades, we have lived an information technology revolution that has been amazing, that has brought to humans a fantastic technology that has completely modified the way that we work, that we interact with each other, or even how we think. This IT revolution is expected to be just, it is expected that we are just living the beginning, because in the coming future, things like 5G, artificial intelligence, the Internet of Things with trillions of sensors connected to each other, etc., is going to be dominating our daily life. And we definitely are living a big data era. And to exemplify this, I would like to share some, what I believe, some mind-blowing data with you. So from 12,000 BC to 2003, the total data generated by humans was of the order of 5 exabytes. So exa is a prefix that means 2 to the 60, which is about 1 million tera. And by 2025, it is expected that we will be generating of the order of 460 exabytes per day. So you can see how the landscape of humans is massively changing due to this IT. However, the technology that is sustaining this revolution is starting to have really important challenges. First of all, the slowing down of Moore's law that dictates the storage density, the number of transistors, let's say, that can be manufactured. This trend that has been valid, it was an empiric law that was valid since the 1960s. It has started to not be possible anymore. So the performance of these devices is starting to plateau. And also there is a big concern about the energy consumed by these technologies. So by 2025, it is expected that the communication industry will be responsible for about 20% of electricity consumption in the world. So there are huge challenges ahead, and it is clear that to solve them, we need new technologies that are based on systems that are not the same systems that were sustaining this technology, and will be needed to be based on new physical phenomena. These systems will need to be also more sustainable, and due to the character of these technologies, they will also need to be multifunctional. So what is the role of magnetic nanostructures in all that? Well, magnetic nanostructures have been at the core of this revolution, complementing all the semiconducting industry. So for those that are not magnetic specialists, we can talk about the magnetic hard disk drive, which is consisting of a track of recording media, where we have a magnetic material formed by grains that store the information, binary information, via the direction of the magnetization. In this case, left or right could be used to store ones and zeros. This track moves very fast, and we can either write or read the information stored by a read head. And the same as transistors, magnetic hard disk drives have followed an amazing evolution over the last decades. So starting from the first hard disk drive created by IBM in 1956 called RAMAC, you can see that it was not precisely portable, to today hard disk drives that are way more capable, they are faster, and they are also much cheaper. So this has been an outstanding evolution of magnetic nanostructures to store information. And you know that you don't have hard disk drives anymore in your computers or in your mobile phones, but still all the information that you access when you go to the internet, or you store information in the cloud, when we do any Google search, is accessing to this type of magnetic hard disk drives. And not only that, magnetic nanostructures are now becoming a very important technology for memory as well, not only to store the information, but also to process that information, to perform operations and so. Thanks to what it is called the magnetic random access memory, which is a memory that is based on this type of multi-layer systems. I won't get into too much detail, but it is non-volatile. So that means that the information is stored there without having to be continuously applying energy, as it is the case for standard RAM that is based on semiconducting devices. And it is fully compatible with CMOS, so it can be directly integrated. The thing is that how does it work, very briefly? Well, we can store ones and zeros, as you can see here, via the resistance of this device, which is called a magnetic tunnel junction. And the relative orientation of one of these two layers that are ferromagnetic, separated by an insulating very thin layer, can be switched via an effect called spin transfer torque that is reliable relying on conservation of angular momentum in the quantum level. So these memories are starting to be now a reality. So the big manufacturing industry is starting to make them massively and investing millions and millions on them, and they are competing already with flash, and they are expected to be a possible alternative for static random access memory. And overall, the one important thing that I wanted to manifest or to make clear during the talk is that the main advantage these days of magnetic nanostructures for computing is that the fact that they are non-volatile. I repeat that. So you can see some work done at Tohoku University in collaboration with NEC, where just by changing the type of the way the standard microcircuits work, integrating this type of magnetic technology permits to cut power consumption drastically. Yeah, so this is just some perspectives, but they are very exciting. And not only that, so I have talked about hard disk drives and magnetic random access memories, but it is there are some proposals still in the lab, of combining new type of physical phenomena in what it is called spintronics, which is this area of using magnetic materials but exploiting the spin, the magnetism of electrons, to create a full computing system that could be just based on spintronic devices. So the whole standard computing pyramid that exists in computers could be now formed by only spintronic devices. This is just some promises. This is still not a reality, but that shows how the field is evolving very quickly. And not only in terms of conventional computing, but also the spintronic community is very active these days on unconventional computing. So going beyond von Neumann architectures and starting to work on neuromorphic computing approaches, where we could get functionalities more similar to what the brain can do than the standard computing hardware. So there are some very promising results in this area that I won't get into detail, but the focus of my talk and of my research is on three-dimensional nanomagnetism. So far we have been talking about very impressive advances that have happened during the last years, and also on future routes of how the spintronic community can contribute to that. However, in all these cases, the type of structures that we are considering are planar. So they are fabricated by standard lithography techniques that are amazing to control very nicely the shape of 2D systems. So where the thickness of these structures is very thin. And is also very good on controlling interfaces between thin films. However, in terms of magnetic materials, that means that the magnetic state, the magnetization of the system, will only depend on the substrate coordinates. So there won't be functionality in the vertical direction. So what we are starting to investigate, and this is the focus of my talk, is the possibility to go into 3D. So instead of having these 2D objects, we are starting to study new types of three-dimensional objects, which are way more difficult to fabricate and way more difficult to characterize than standard 2D. We need to fabricate them with a control that is of the order of hundreds to tens of nanometers, because we need to be able, the same way as in 2D, to control the shape of these structures on length scales of the order of the magnetic characteristic lengths, which is of the order of tens of nanometers. And we are doing great progress in this way, in creating new synthesis and new characterization and computational tools for that. And this is opening us an amazing new area of new physics driven by this change of dimensionality. Thanks to this new physics, logically, we are also looking to the possibility to, in the future, exploit them in new applications. So this leap to 3D is a general trend of nanotechnology that brings really great challenges, but also great opportunities. So let me briefly show you a taster of what type of new magnetic effects emerge in 3D, because we are talking about new physics. So what happens when we go into 3D? Well, we are going to get new types of magnetic states, what we tend to call spin textures. So complex magnetic configurations that do not exist in 2D. And because now we have a system that has more degrees of freedom, can have this type of new spin textures. We can control things like topology or curvature to control these spin states, something that is not possible in 2 dimensions. And also the fact that these systems now behave differently opens a route, for example, to make the possible devices faster. So things like magnetochiral effects could be exploited to overcome fundamental limits in terms of speed that exist in 2D. So many of them, of these ideas that I'm bringing are still theoretical predictions, but there are recent advances in this area, and I will show you what my group has been doing in this realm lately. So just to wrap up this first general introduction, I would like to state that I believe that 3-dimensional nanomagnetism, which is this emerging field, is very promising for future green technologies. And this is something that we reviewed, and we gave some ideas of how the field could evolve in the coming years in a paper in Nature Communications a few years ago. So, for example, we show in the paper a futuristic view of a possible 3-dimensional nanomagnetic Internet of Things chip, where we would have many complementary devices integrated in the same chip, including 3-dimensional ultra-high data storage, areas for neuromorphic computing, or areas where we could make a lab-on-a-chip it will have lab-on-a-chip capabilities, including sensing and so on. So with this, I come to the main outline of my talk. So I would like to just give you an overview. I won't get into a lot of detail in any of these 4 areas, but I would like to give you an overview of how we have created recently a new framework to 3D print nanomagnetic structures, how we can move magnetic information in the form of domain walls in 3-dimensional nanowires, how we are starting to investigate new effects in 3-dimensional nanomagnetic circuits in terms of magnetoelectrical signals, and finally some ideas about how to control the magnetic chirality using geometry only. So together with the 4 areas, I include as well the key article published in each of these sections in order to give you, if you are more interested in any of them, you can look at it later. Okay, so let's start with the first one, which is about 3D printing of nanomagnets. So first of all, I would like to introduce this nanolithography technique called focused electron beam induced deposition, for short FEBIT from now on. This is a technique that I learned during my PhD under the supervision of Ricardo Ibarra and José Mari de Teresa in Zaragoza, and that I have been expanding during the last years. It consists on the following. It is done in a scanning electron microscope that has a pattern generator that can control a focused beam of electrons of nanometric in size. And together with that would be the standard thing for an electron beam lithography system. We have a gas injector system, or GIS, that introduces gas into the SEM chamber, with this gas getting absorbed on the substrate in such a way that when the beam of electrons scans or gets focused on one of these points, it breaks locally this gas, creating volatile molecules that are pumped away and leaving a deposit behind. So you can think about FEBIT as a local chemical vapor deposition, which is induced by a focused beam of electrons in the kilo electron volt range. Why are we interested in this technique? Well, it is a one-step lithography process process. So we don't need, as standard lithography methods, any resist or template to fabricate nanostructures. We can grow systems on almost any substrate. So it is very versatile in that respect as well. And it has a great performance for 3D nanofabrication, as you can see in this beautiful example by a group in Austria, where they are scanning the beam, and when you stay for some time in a particular spot, that deposit will start to grow, right? In comparison with other direct additive manufacturing tools that can grow metals, FEBIT is the one that has a better resolution. So we can pattern nanostructures with great accuracy. So this is not a technique for mass, for really high volume of the position, because each structure is done one by one, but it's a unique tool for nanoprototyping that opens a new route to study and explore physics in three-dimensional nanostructures. In terms of materials, FEBIT, this has been always the main drawback, particularly when we face the deposition of non-magnetic materials. Imagine that you are using this standard organometallic gas, which is typical for CVD, containing platinum. And due to the low decomposition efficiency of FEBIT, normally you will end up getting a deposit that is has only of the order of 15 to 20% metal in atomic percentage, with the rest being carbon and oxygen. So basically this is a dirty material, although there are new ways to create, for example, platinum and gold FEBIT materials using other methods that can be post-growth or injecting as well reactive gases during growth. The good news is that if we use this type of organometallic gases that contain ferromagnetic metals like cobalt and iron, or even a combination of both, it is possible to directly create by FEBIT metals that are 85 to 95% pure. This is actually was one of my main results during my PhD, where we observed this for the first time, so that we can directly write functional ferromagnetic materials with this technique. If you are more interested in what type of purities and what type of systems have been studied so far, you can see here these two reviews on 2D and 3D systems in collaboration with Jose Mari de Teresa. So let's focus then on FEBIT for 3D nanofabrication. As I said before, this technique is unique for 3D nanofabrication with nanometric resolution, and there has been really fantastic progress over the last years in this realm. So you can see here two examples from the group of Jason Folks and Michael Ut, where they have created software that is able to create these complex three-dimensional nanowire-based systems where the nanowires are interconnected, creating this type of lattices. This is absolutely fantastic, but it doesn't give us still the great flexibility that we would need to study three-dimensional nanostructures, where we want to go beyond these structures that are formed by 3D nanowires and create arbitrary 3D geometries. So for that, we have created in my group a new framework for 3D printing by FEBIT at the nanoscale, and this has done by Lucas Koric, which is a PhD student in Cambridge. So the idea is the same as a 3D printer. We want layer by layer grow any complex 3D object. We need for that to take into account that each deposit in one layer is interacting to each other via proximity effects. So for that, we will need to take into account that in order to grow a particular layer height, we will need to consider not only the growth rate at a given point, but the time that the beam has been scanning in a point and how that affects the deposit nearby. So in order to do that, we have developed this rigorous framework that is based on previous work, also in my group, where we describe what it is called the FEBIT continuum model that describes the process of growth in FEBIT by using these characteristic frequencies that define all the processes happening during a FEBIT growth for adsorption, dissociation, desorption, and diffusion. And under particular conditions that we can realize experimentally, we can we can basically obtain what is the growth rates as a function of these characteristic frequencies, with these characteristic frequencies depending on experimental parameters that we can control. So together with that framework, we have also developed a simple calibration procedure that allows us to access to the different components, the different factors that determine the height of a deposit. So we have developed a simple two-step calibration procedure where we can obtain the growth rate obtained at the substrate surface where there is a particular temperature. And then we have developed another step in the calibration that allows us to know how much is the sigma, basically the width of the deposit, so that how that is going to be affecting neighboring deposits, as I explained before, when we grow a given layer. We also need to take into account when we grow 3D nanostructures that these systems can get high temperatures. And in some cases, we need to take into account that this sublinear growth regime that we obtain here is due, or it can be modeled by this K factor and this thermal resistance temperature that we can automatically calculate in our software for any 3D geometry. So once we have developed this framework and this calibration procedure, we can grow any particular nanostructure. At least that's what we want to see. So for that, we have, this is the interface of the software that Luca has created. And this is a given 3D object that is particularly interesting, that has some two types of curvature that is interesting for nanomagnetism. This 3D object can be created by any CAD software such as AutoCAD, FreeCAD, or Inventor. We plug it into our software, and then we do basically the same as we would do with a 3D printer. We slice this system, this object. We, using our algorithm, we calculate how much is the expected temperature increase that has been determined by the calibration procedure, and we can then calculate how much is the dwell time. In other words, how much time the beam needs to be on each spot in order to create a given 3D nanostructure. And you can see how, in this case, is a platinum-based nanostructure. We get a very nice agreement between the design and the experimental realization. So we have tested this algorithm and the computational program for two precursors. Both work very well with some differences, for a range of 3D complex geometries with features down to hundreds or tens to nanometers, and in three different microscopes, and achieving good results for each of them. So let me show you some examples of 3D printed Febile nanostructures that we have created. First of all, starting with nanocubes that are based on nanowires, the same approach that we saw before done by other groups. These grow nicely in a few seconds, but we can also grow way more complex 3D nanostructures that we want to investigate, such as a Mobius strip. So this is a cobalt Mobius strip. This is the CAD file, and this is the SEM image where we have been imaging the structure at multiple angles and seeing how this grows very nicely. So we get resolutions down to hundreds of nanometers for complex 3D geometries, and even below 50 nanometers for objects based on nanowires. So the algorithm works really well. So we were really happy with these results, but we wanted to challenge how far could we go. And for that, we were thinking about what structures, what type of a structure could we grow that was particularly challenging. And in order to understand this experiment, I need to go back to the past and put this experiment in context. So this is a picture of the Cambridge University basketball team in February 2013. This is a timeout. And if you look closely, you will see that this is me. So I was the coach at that time of the team. And this is Luca, who before being a PhD student in Cambridge was a great basketball player. So Luca and I share the same passion for basketball. So what we decided to do is to create the hand of Stephen Curry after scoring a three-pointer, but about 50,000 times smaller. logically, the hand, now getting serious, is a very interesting system because it has many scales, many different curvatures at different scales, many features that are going to be very challenging for our algorithm. So Luca definitely accepted the challenge, and these are the results where we have the design and the other steps that I explained before. And you can see the final SEM image of the structure that we managed to grow in about 1 hour. This was done in Glasgow in June 2019. This result shows the great performance and versatility of this new algorithm to 3D print nanostructures by Febit. It is also an interesting structure because this is a volume, it's not a surface as other structures that I have been showing before. And volumetric structures will require going a bit beyond, to polish a bit more our algorithm, going beyond proximity effects in one single layer. But these will be things that we will develop in the future. Right, so after having talked about 3D nanofabrication, let me start to talk more about magnetism. And the first result that I would like to share was done a few years ago, where we were investigating the motion of domain walls in 3D nanowires. So first of all, I would like to contextualize a bit for the non-experts in the room what are magnetic nanowires and domain walls. So as I explained before, for hard disk drives, magnetic information is stored by the relative direction of the magnetization, thinking about right domains storing a 1 and left domains storing a 0. So if you now think about magnetic nanowires, it is a very elongated system where we will have nanometric dimensions in width and thickness, but micrometric dimensions along length. So that means that the magnetic bits or the magnetic areas can break into multiple domains, storing a long sequence of bits. And each in between these domains, we have what it is called a domain wall. So domain walls are very interesting systems because when we apply external inputs such as magnetic fields, electric or spin currents, strain, thermal gradients, it is possible to move them along the nanowire length. So if you imagine now a system where we can write magnetic domains on one side of the wire and read them at the other side, and we have this motion of domains synchronously with an external clock, which would be given by this external input, we can have some kind of shift register. So magnetic circuits are very impressive, or they have been really under a lot of investigation because they are very interesting from a physical point of view, but they are really promising for future applications. So what has been done so far? In terms of 2D nanowires, or nanowires that have been patterned by conventional techniques and that they are planar, as I explained before, there has been a lot of investigations. So they have been realized in the lab, and they have it has become possible to do logic with them, to store information using domain walls or other type of magnetic objects called skyrmions, or also the possibility to transmit information using spin waves that are excitations of the magnetic state. It's not only that they have been done in the lab. IBM developed a prototype several years ago, what it is called the Racetrack Memory, where they showed good functionality. And there's also a commercial product that is a sensing device that measures the turns of a wheel in a car for a multi-turn counter. No? So this has been done in 2D nanowires. However, it would be really an amazing technology if it was possible to realize this type of 2D motion of domain walls, but on 3-dimensional nanowires. In nanowires where we would have the wires out of the plane of the substrate, because we would have ultra high density storage in these systems, and we would have really great functionalities complementing existing computing devices. However, as I explained before, this has been proposed for many years now by Stuart Parkin at IBM, but it is extremely challenging due to the fabrication and characterization challenges that that exist to do these 3D systems. So in this work, we were investigating the first steps towards realizing this type of device. And we created these three-dimensional domain wall conduits, where with FEBIT, we fabricate with a non-magnetic precursor a three-dimensional nanowire, as you can see here, which is a non-magnetic scaffold. And then we evaporate a magnetic film, in this case, nickel iron, which has very good properties for domain wall motion. So we are using not only FEBIT, but here a hybrid method combining FEBIT with a physical vapor deposition method that gives us high quality in the magnetic material that we are integrating into the device. So you can think about it as a three-dimensional nanomagnetic conduit, where we will have a source of magnetic information, which is the thin film. We will have a 3D conduit, which is this 3D nanowire, and then we will have a 2D to 3D interconnect that will be key in order to transmit this magnetic information into 3 dimensions. We realized experimentally this system using FEBIT and evaporation of nickel iron. You can see here one system. This is about 300 nanometers. We can do it now down to 50 nanometers if we want. And we have paid particular attention to the interconnection, because this is a critical area that is going to limit the smooth motion of domain walls in our devices. So, okay, you have seen that we have a really great ability to 3D nanofabricate these type of systems, but there's another huge challenge here, which is how can we probe this system? Because you will imagine that this is a very small 3D nanostructure embedded in a sea of magnetic film. So traditional nanotechnology tools won't be able to measure easily this system. So for that, we have used the magneto-optical Kerr effect, or MOKE, which is a technique that was developed by John Kerr in Glasgow in the late 19th century, that is exploiting the change in polarization of light when reflected from a magnetic material. The light rotates its polarization, and it also acquires some ellipticity. This is a standard tool to probe and image the magnetic state of planar magnetic systems, 2D systems. In particular, it is very good for nanostructures because it has a very high sensitivity. So in this work, for the first time, we developed or we expanded MOKE to measure 3D nanostructures, and we call this technique the dark field MOKE. And it consists on the following. So we will have the standard optical path where we send polarized light to our system, and we will collect with a detector the change in polarization via polarizers that results from the reflection from the film. But a very tiny proportion of this light will also be reflected at a different angle via specular reflection due to our nanostructure that is grown at a well-defined angle. So this is what we all can also collect and analyze with polarizers in this dark field detector. So we fabricated, we built this system where we also added the possibility to apply magnetic fields in any direction of the space. And these are some results where we show how we can independently and simultaneously detect the switching under magnetic fields of a film that has been fabricated, and also of the nanowire. So this is a beautiful new technique to study three-dimensional nanostructures that we have developed. And what my PhD student at that time, Dedalo, was doing, he developed, he built part of the system, and he also did fantastic work where he was characterizing this type of three-dimensional nanostructures under magnetic fields. So I won't get into a lot of detail because this, the characterization of these devices is not trivial, but we can apply magnetic fields along three directions of the space that gives us access to different characteristics of the device. We can understand how the domain walls propagate. We can understand how well this injection occurs by applying Y fields, and we can also measure what is the reversal mechanism by applying Z fields. And these are some selection of experimental results where you can see that we characterize the switching of the nanowire and of the film with the two types of detectors that I explained before simultaneously as a function of HZ offsets and applying HX fields. But we did it also not only for the domain wall conduit structure that I explained before, where we have interconnection in between the film and the nanowire, but also for other type of in-purpose grown structures that serve as control, where we disconnect the film from the nanowire in order to understand how the switching of this system works. So thanks to the deep understanding that we got from the device, we could design experiments where we were gating the domain wall injection of from the film to the nanowire by applying external magnetic fields. And this was the first experimental realization of domain wall injection into a 3D nanowire conduit. So thanks to the development of the dark field MOOC and these new results on domain wall injection into 3D, Daedalus received the Abdus Salam Award in 2017 for the best PhD work at the Cavendish Lab of the University of Cambridge. Right. Okay, so I still have a bit of time to talk about two more things that I would like to show. You see that I'm not getting very deeply into any of them, but I just want to give you more of a perspective of some things that we are doing at the moment on this field. The next that I would like to show you is very recent results published on ACS Nano. I think that it was last week, where we have been investigating some unconventional magnetoelectrical signals in 3D circuits. So this work has been done by my PhD in Cambridge, Fan Meng, and Claire Donnelly, a postdoc fellow there, where we have been investigating this type of nano circuits, which are some bridges, where we have integrated them into a microelectronic circuit fabricated previously by a standard optical and focus ion beam lithography. So we have grown with Febit this type of nano bridge that you can see here experimentally. So this is a side view and top view SEM image of the device, where we have this nano bridge and where we are able then to apply current through the circuit and measure the voltage drop that gives us information about what type of 3D magnetoelectrical effects occur in this geometry. So we have studied the type of reversal mechanism that exists in this type of system by applying external magnetic fields, as you can see in this simulation. And due to the geometry of the bridge and how we have arranged the contacts gives us a very compact and stable 3D circuit that can connect very nicely different parts of a 2D circuit. But it is clear that due to this geometry and the arrangement of the contacts, we are going to get a superposition of different magnetoelectrical effects. In particular, we expect the contribution of standard magnetoelectrical signals in a ferromagnet, such as the anisotropic magnetoresistance and the Hall effect, both anomalous and ordinary. These are well understood magnetoelectrical signals that were found for the first time by Lord Kelvin in Glasgow and Edwin Hall in Harvard in the late 19th century. The AMR briefly is basically giving me a change in resistance due to the relative orientation between the magnetization and the current direction due to spin orbit coupling. And also due to the spin orbit coupling, we have the anomalous Hall effect, where we have a different, an accumulation of transverse voltage in a ferromagnet when current is flowing through it in the presence of a perpendicular magnetization that can also be probed. So, okay, so this is the type of signals that we would be typically expecting in our nanowire circuit. And we studied them as a function of a magnetic field that was applied at different angles with respect to the substrate plane, as you can see here. We did some symmetry arguments to find both longitudinal and transverse voltage. I won't talk about this. I will just focus on the magnetoresistance signal in this talk, where you can see the type of shape that we get for different angles. And this is the experimental results that we obtain at 4 Tesla. So you see, this is the angular dependence that we have in the magnetoresistance as a function of theta. And you can see how, if we just take into account the anisotropic magnetoresistance, we would not expect for this signal Hall effect. We would just be expecting AMR, but you can see that the dependence that we would obtain according to our initial simulations are by far very different. They don't correspond to the experimental data. So what we did was we had to consider another contribution that is not that standard, which is the magnet-magnetoresistance. And you can see that when we consider it, we can get a really nice fit to the data when we add both AMR and MMR. So we have a large contribution of magnet-magnetoresistance in our device. And why is that? Well, magnet-magnetoresistance is measuring the amount of spin waves generated in our system. In other words, the spin disorder that we get typically due to thermal excitations in our ferromagnet. And it will be directly proportional to the effective field that we get, that we have over our material. The effective field is an addition of the spontaneous magnetization, the external magnetic field, and the so-called demagnetizing field that comes from magnetostatic interactions. So the point that I would like to make here is that when we have a three-dimensional circuit, due to the non-trivial demagnetizing field, due to the geometry that we have here, leads to way more complex angular dependence of the magnetoresistance that we could obtain in a 2D circuit. And this is something that we are going to need to take really into account when we start to design our 3D magnetic sensors, for example. Yeah, we will also have a very important contribution in general of the magnet-magnetoresistance. And in this work, Fan and Claire found this for the first time. Okay, so I still have a few minutes, so let me now finish the talk by talking about the geometrical control of magnetic chirality that we also recently got in this paper published last year, where we have been able to imprint chiral spin textures and topological defects exploiting 3 dimensions. So first of all, let me briefly summarize what is chirality. So chirality refers to the property of structures that cannot be superimposed on their mirror image. So if you think about your hand and you mirror it, you know that they are not going to overlap to each other, and this means that they are chiral. Yeah, this is a property that is really important in nature. It's almost everywhere, and has been recognized as really key for things such as the origin of life, not less. It is present, for example, in DNA or in molecules that give properties such as its flavor, its toxicity, its drug efficiency, and so on. What about magnetism? Well, when we talk about chiral magnetism, we are referring to how the magnetization rotates when it goes from, for example, think about up and down spins, if it is doing this rotation either clockwise or counterclockwise. So these two systems have two opposite chiralities, and in general, magnetic materials are achiral. So they don't have a well-defined motion of the spins, or if there exists this well-defined motion of spins, both chiralities are degenerating energy. It doesn't matter if they do it one way or the other. However, it has been recognized recently in the last years that it is possible to design some magnetic structures in such a way that it is possible to favor one of these two. One of them is going to be energetically favorable than the other. And this is what it is called the Diallo-Sinski-Moria interaction, or DMI, which is an antisymmetric exchange interaction. For that, we need asymmetry breaking and also spin orbit coupling together. This can be obtained in some bulk materials, but mostly in spintronics is these days realized by interfacing magnetic layers in an asymmetric way to heavy metals. This is the standard way to do it, where the heavy metal is bringing a very strong spin orbit coupling. So magnetic chirality is really key for spintronics. Any or almost any device these days is relying on spintronics. For example, for the Racetrack Memory, it is really key to have unidirectional motion of domain walls at low currents. So as you can see, this is how the magnetic community is creating chirality, which is this very important property that we need for spintronics. But now we can pattern nanostructures in 3 dimensions. And that brings a really important point as well that I would like to make, is that now we can start to think completely out of the box and, for example, see how nature is creating chiral structures. So if you think about DNA or, for example, this plant, they use helical geometries. So they use helical geometries because that has an intrinsic chirality, and this gives some very important properties to these systems. In this plant, for example, it is also important to mention that the chirality can change in a very localized area, what it is called in nature a tendril perversion, going from left-handed to right-handed. This gives some flexible properties that are important for this type of plants. Okay, so taking an example of nature, we decided to create such a complex chiral magnetic structure using our unique nanofabrication techniques. This was nicely done by Dédalo Sanz, Aurelio Hierro, and Claire Donnelly. And we created this type of double nano helix grown by Febit that is made of cobalt. Yeah. So this is a color SEM image of the system where you can see the two strands. You can see that the two strands overlap to each other, so they are really touching. So we can control both magnetostatic and exchange interaction in this system by this overlapping. And we have created the system as the same as the plant that I showed you before, with a tendril perversion. So we have a change of the chirality of the system halfway through the structure. And you can see that, in this TM image that we can control it really with very nice nanometric resolution. So we then decided to study how does this structure behave magnetically. And for that, we went to ALBA Synchrotron in Barcelona, where they have this very impressive soft X-ray transmission magnetic microscope that exploits a phenomenon called X-ray magnetic circular dichroism, which is very similar to the Kerr effect that I explained before, but in the X-ray wavelength. So in such a way that we can get magnetic images of the system that we are investigating at about 30 nanometer resolution. And the microscope is designed so that we can study the system at multiple angles. This is what we exploited experimentally. I will just show you a snapshot of one of the experiments that we got, where we can see our double helix. This is the area of the tendril perversion, and you can see an alternating magnetic contrast of XMCD between red and blue. And this corresponds, if we look at our simulations, with the fact that we have the strands anti-parallel to each other and a domain wall halfway in between both the strands. So what does it mean that we have a domain wall in between the two strands? Well, the best way to understand this is to visualize what is the magnetic chirality of the system across the length in our simulations. So you can see this is the domain wall that I was talking about. And the beautiful thing of this work is that thanks to 3D patterning, we have been able to locally control the magnetic chirality first. So the domain wall chirality, this domain wall is chiral, going from down to up magnetization. The way this transition occurs is chiral, and the chirality is directly described by the geometrical chirality of the helix. And secondly, we can, thanks to the fact that we are changing locally the geometrical chirality of the helix, we can imprint very complex magnetic textures in that area. In particular, we observe in our experiments that we can create what's called a 3D vortex, and a 3D vortex, and also a Nell defect that interfaces both type of chiralities. So we can not only locally control the magnetic chirality of our textures, but we can also form localized topological defects at well-defined areas, something that is not possible with the ways that I explained before in two-dimensional nanomagnetism. Right, so with this I come to the conclusions. I have shown you that three-dimensional nanomagnetism is an emerging field with a huge range of new phenomena to be explored, and it has a great potential for future computing applications. And I have shown you, I have given you an overview of some of the activities that my group has been doing over the last years in this area. If you are more interested, please take a look at these publications. I would like to thank the fantastic work of all my group at the University of Cambridge and at the University of Glasgow that have made possible all the results that I showed today. Also our funding bodies and also all the collaborators in many groups across the world. And I would finally like to say what Scott was mentioning, that I plan to continue doing this work on three-dimensional nanomagnetism at the Institute of Nanoscience and Materials of Aragón in Zaragoza. And particularly from October 2021, I will start an ERC consolidator project called 3D Nanomag that will focus on this. If there's anyone in the room that is interested in a postdoc or a PhD position, please contact me, and you can also look at my website where you can get updates and learn more about three-dimensional nanomagnetism. And with this, I finish. Thank you so much for your attention. Questions?
Thanks very much, Amalio. That was a really incredible talk. Quite a stellar, very cool talk. I thought you made it very accessible and informative, and it was very inspiring as well. You know, going from 19th century physics to real frontier research. It's very cool, really nice. And, you know, for me who understands nothing about magnetism, I felt for a second like I understood some things there. So that was really nice. So thanks very much for doing that. Does anyone have any questions? Would anyone like to, I've posted in the chat that please just write in the chat, or okay, here's someone in the question answer. Jose Mari, okay, let's see if I can open your mic, Jose Mari, just a second. Jose Mari, I think you should be able to talk. If you all you need to do is unmute your microphone and you should be able to ask your question.
Okay. Can you hear me?
Yes.
Yes, perfectly.
Okay, great work and great talk, Amalio.
Thank you,
one question about the materials. So maybe cobalt is not the best material for 3D nanomagnetism because the domain walls are wide and maybe they are slow. So what is your perspective on this? Do you have in mind other materials for 3D nanomagnetism?
Yeah, so as you well mentioned, any device that is based on controllable motion of any spin texture, cobalt is not a good alternative. So cobalt can have applications in 3D nano devices where this is not the mechanism that is exploited. And you saw that from the beginning, where we wanted to study any motion of any texture, we decided to go to this hybrid nanofabrication method. And this is how I see it. I think that the combination of FEBIT or other 3D additive manufacturing tool in combination with other more standard techniques is the way to go. Which also brings other challenges. But I expect that things like electrode deposition, electroless deposition, atomic layer deposition in combination with FEBIT could be a good option. But okay, I think that the spectrum is quite wide, so it depends on what you want to do. And yeah, a hybrid nanofabrication method is probably the way to go, at least for the moment, because I think that is very encouraging that this new cobalt iron precursor was synthesized recently. This brings quite a lot of excitement in the way that the synthesis of more advanced precursors could be developed that brought a wider variety of magnetic materials, but we are still a bit far. Yeah.
Thank you.
And Ricardo Ibarra, I'm going to unmute your microphone as well. You should be able to unmute your microphone and ask your question, Ricardo.
We cannot hear you, Ricardo. I don't know if you're muted.
You'll have to unmute yourself manually before you can ask your question. maybe there's a technical issue there. If you do have any problems, Ricardo, asking your question, you can always write it in the chat. Okay, we'll come back to Ricardo in a second. Can I ask you a quick question, Amalio?
Yes, of course.
Maybe this is a ridiculous question, but I've read recently quite a lot about things like magnetotactic bacteria, and you talked a lot about 3D nanomagnetism as like a future green technology. Has anyone looked at things like magnetotactic bacteria for the growth of 3D nanowires for technological applications? Because I can see obviously why that sort of thing would be much less precise, but it could also help to introduce things like chirality into these nanowires.
Yes, this is not at all a bad question. Yes, so this has been something that has been on the radar of quite a few people in magnetism, and I know all works on this in the past, and there has been recently some works on characterizing nanoparticles and also this type of systems. From the top of my head, I don't know if someone is really doing that right now, but I think that it has been proposed. Yeah, so it is, I think that we are using here, and I showed you here a very unique way to 3D pattern, but this is logically not gonna be the way for many applications. And what you are proposing sounds like a very sensible, futuristic way to do it. Yeah. I think that the future could be there, or other ways of self-assembly or other methods. Yes.
Thanks very much. Yeah. Maybe we can talk about that when you're over. Luis just says congratulate you for your talk. Very nice. Does anyone else have any questions? I have lots of questions about the difference between working in the United Kingdom and how it's been over there for the last 11 years and what you're looking forward to coming back here to Zaragoza, but maybe we can chat about that over a coffee or a beer once you're here.
Perfect, yeah.
Has it been very difficult coordinating your team in Cambridge and Glasgow over the last year? I can't imagine how hard that must have been.
Well, I think that I would say that I was better adapted to be delocalized than others. So in that sense, it has been, I have had a small advantage. But yeah, I think that my group, I was telling them the other day actually that they have been outstanding on getting adapted, and we are using Zoom all the time to be able to interact and to continue moving things forward. But yeah, not simple, yeah.
Okay. I think David Serrati has a question for you. I've opened your mic, David.
Yes. Can you hear me?
Yes.
Yeah, so I also had to congratulate for this excellent talk and work and proposals and so on. Maybe because the discussion came now to the social matters, maybe I look like a freak if I come back to the science. But anyhow, my question was about once you can do chiral textures and curvatures in 3D geometries, okay, with your precursors. I was wondering if, because this would be really a very important step forward in the case of other materials like bismuth, or like even topological insulators like mercurium telluride and these kind of things. Yeah, maybe mercurium telluride is too much, but why not bismuth? Because with a curvature, you know that you can induce spin textures, just because of the curvature, in this kind of strong spin orbit materials with rush backup. So, are you thinking in trying to grow some, the rest of the periodic table, like bismuth?
Yes, so I think that relates closely. Thank you, David, for the question. That's great. So it relates quite closely to the question by Jose María de Teresa. I think that the challenge here with this particular technique is the quality of the materials that you can grow and the type of materials that you can grow. As far as I know, no one has ever fabricated with FEPIT any bismuth system. It's also very dirty. We need to also take into account that the precursors that we can put in our microscopes, unless we have a specific microscope for molecule development, are very sensitive to all this dirt that is generated, and bismuth is particularly not a nice element. So I think that I would say that you're touching one of the key areas where FEBIT could be really, if there's a strong collaboration, as there was, or at least it was attempted in the past, and there were very nice results out of them from a project called Selena, that it was a European project where chemists, physicists, engineers, they put all their energy together in order to create new types of molecules, and we study their performance, the way they decompose, the associated resolution that we can get, the growth rates, how dirty it is for a microscope, and so all that work is needed. And I think that is a route that, with the with the precursors that I show you of cobalt and iron, I think that we are really, let's say, giving a great example for how the community can go in that area, right? We are showing that if we are able to create that type of purity, we can do absolutely outstanding things with those materials. So it is important, as you say, that there is a complementary development, but that requires a multidisciplinary team to create new precursors that can expand other areas. And bismuth could be a fantastic choice. I agree with you, yes.
Thanks, Amalio. Ricardo has his microphone open. I think he has a question for you.
I think so. Can you hear me?
Yes, we can, Ricardo, yes.
Well, at the end. Okay, hola, Amalio and everybody. I'm very happy to hear your presentation and know about your progress in this field.
Thank you, Ricardo.
I would like to, if it would be possible for you to comment about the purity of your nanostructure. From the beginning, this was something that we were very worried about. Mm-hmm. And I'm sure that this has been improved a lot, even if it's difficult to improve more than this. But also about another issue, which is the domain wall speed in your nanowire and your nanostructure. And mainly when you have the combination between this thin film and the nanowires, in which the domain wall could propagate a completely different speed, if I are right. Mm-hmm. Could you comment on both things?
Yes, yes. So regarding the purity of the wires, so clearly the best choice for us in terms of purity these days remains being the precursor that we studied together during my PhD, which is the cobalt octacarbonyl. So this is the precursor that gives so far the best purities. And we see when we pattern on 3D some aspects that don't exist on 2D. For example, the thermally driven autocatalytic effects that happen. So the fact that we are growing in 3D makes the deposits, as I explained during the talk, get hotter. And we are observing how that can lead, under particular conditions, to autocatalytic growth. That means that the purity that we are going to get in these objects is almost purely cobalt. So this is one thing. The other thing about the purity is that we also play with mild post-growth procedures to improve a bit the magnetic properties. So this work has been done by Aurelio Hierro in my group, where he grows a nanostructure and then he has performed different type of annealing procedures, and we can see directly from spectrum how the metallic peak of cobalt gets better defined, and we believe that there is a better exchange coupling in between the grains due to the migration of carbon impurities from the center of the deposit towards the surface. So these are two things that I think that are particularly newer and that lead to relatively, I could say that, I wouldn't say pure materials, but really functional cobalt nanostructures. But as I explained before in the answer to Jose Mari, this doesn't mean that this is the best material to do things like domain wall motion. So in terms of domain wall motion, that was your second question, you're absolutely right. So the change of geometry from a planar-like rectangular shaped cross-section to other types of geometries and topologies may lead to a way faster motion of domain walls. So in other words, this may inhibit the so-called Walker breakdown. So the Walker breakdown is an instability that happens when I start to move my domain walls. There is a moment where in a rectangular shaped wire, we get some instabilities that make the motion very unstable. So the domain wall breaks and you start to have back and forth motion, chaotic motion. You may even have at very high speeds. So that typically limits your speeds to 100 meters per second. That's the rule of thumb. And the fact that now you can grow structures with a different cross-section, let's say like a tube, no? Like if you had a tube, for example, would be a nice example, that is expected to inhibit the Walker breakdown. And that should lead to domain wall speeds that could be one order of magnitude higher, like 1,000 meters per second, get to the Magnonic regime, get the Spin-Cherenkov effect. So there are some theoretical predictions there that are really interesting. There has been, I would say, that outstanding work by the group of Olivier Fouchard in Grenoble about this, where they have seen already that they have very high speeds in nanowires, not in nanotubes, but in nanowires. Okay, they have some transformations and some influence of Ørsted fields that they didn't expect at the beginning. So I think that there is a lot of interesting work to do in that area on the dynamics. I fully agree with you. I think with regards to the 3D nanofabrication.
Muchas gracias y deseando tenerte por aquí.
I don't know if you can you hear me? Yeah.
Sí.
Okay.
Can you hear me?
Yep, thanks, Ricardo.
Okay.
1 second, because I cannot hear you now.
The problem is with Amalio.
Can you not hear us now, Amalio? I think at the moment, can you hear us now?
Yes, sorry, I had a technical problem. Solved.
No problems.
Nada. Gracias y deseando tenerte por aquí, Amalio.
Gracias, Ricardo. Un abrazo.
Igualmente.
So I can't see any more hands raised. If no one else has any more questions, just like to say once again, Amalio, thanks very much. That was a really fantastic talk. And we're looking forward to having you over here in Zaragoza, not long to go now.
Perfect. Thank you very much, everyone.
Thank you very much. And we'll see you over here soon.
Yep. Thank you.
Bye, everyone. See you next month.